There's a place in the universe so cold it shouldn't exist. A cosmic deep freeze that breaks the rules of reality itself, where temperatures plunge below the background hum of empty space. It's colder than the void between galaxies, colder than the darkest reaches of interstellar night, colder even than the leftover whisper of the Big Bang that permeates every corner of existence. That place is the Boomerang Nebula, and its existence poses a question scientists struggled with for decades. How can something be colder than nothing? To understand what makes this distant cloud of gas and dust so extraordinary, we need to grasp something fundamental about temperature itself. Most of us think of temperature as a simple measure of hot versus cold, a number on a thermometer that tells us whether to grab a jacket or turn on the air conditioning. But temperature is actually something far more profound. Every object in the universe, from the coffee cooling on your desk to the distant stars burning in the night sky, is made of particles in motion. Atoms vibrate, molecules spin, electrons orbit their nuclei in endless dance. Temperature is the measurement of all this microscopic chaos, the average kinetic energy of countless particles jittering and bouncing against each other. Hot things have particles moving frantically. Cold things have particles moving slowly. Simple enough. But here's where it gets strange. If temperature measures motion, and you keep cooling something down, slowing those particles more and more, there must be a point where they can't slow down any further. A bottom limit, the coldest possible temperature. Scientists call this absolute zero. On the Celsius scale, absolute zero sits at negative 273.15 degrees. On Fahrenheit, it's negative 459.67 degrees. But Lord Kelvin, the 19th century physicist who first calculated this ultimate cold, created a temperature scale that starts at this theoretical minimum, 0 Kelvin, the point where thermal energy reaches its lowest possible value. Now, quantum mechanics throws a wrench into this neat picture. Even at absolute zero, particles don't actually stop moving completely. They retain what's called zero-point energy, a sort of quantum jitter that can never be eliminated. The Heisenberg uncertainty principle demands it. You can't pin down both the exact position and momentum of a particle simultaneously, so even at the coldest possible temperature, atoms must maintain some residual vibration. But that's a technicality for quantum physicists to worry about. For our purposes, absolute zero represents the ultimate cold, the cosmic floor beneath which no temperature can fall. And the Boomerang Nebula comes within a single degree of reaching it. The nebula sits 5,000 light-years away in the constellation Centaurus. To put that distance in perspective, light traveling at 186,000 miles per second would need 5 millennia to make the journey from that cosmic refrigerator to Earth. When the photons we observe today left the Boomerang Nebula, human civilization was just beginning to emerge from the Bronze Age. At the heart of this frozen cloud lies a dying star, once similar to our Sun, but now in its death throes. For billions of years, it burned steadily, fusing hydrogen into helium in its core, maintaining a delicate balance between the crushing inward pull of gravity and the outward pressure of nuclear fusion. But eventually, like all stars of its size, it exhausted its hydrogen fuel. What happened next follows a familiar stellar script. The core contracted, temperatures rose, and helium fusion began. The outer layers of the star expanded dramatically, transforming it into a red giant. This is the fate awaiting our own sun in about 5 billion years, when it will swell to engulf the inner planets, possibly including Earth. But the star at the center of the Boomerang Nebula took an unexpected turn. Instead of shedding its outer layers at the normal leisurely pace observed in most dying stars, this one began hemorrhaging mass at a staggering rate. Over the past 1,500 years, it has ejected nearly 1.5 times the mass of our entire sun. That's not just fast, it's catastrophically, bewilderingly, impossibly fast. The central star loses mass about 100 times faster than the other similar dying stars. Compared to our sun's current rate of mass loss, it's shedding material 100 billion times faster. Every year, it throws off approximately 1,000th of a solar mass worth of gas and dust. This violent expulsion creates winds that scream outward at 500,000 kilometers per hour. That's 310,000 miles per hour, fast enough to cross the entire United States in less than 10 seconds. These aren't gentle stellar breezes. They're cosmic hurricanes, blasting matter into space with unrelenting fury. And this is where the cold comes in. When gas expands rapidly, it cools. This isn't some exotic quantum effect or mysterious cosmic phenomenon. It's basic thermodynamics, the same principle that makes your aerosol can cold after spraying, that allows your refrigerator to work, that causes the air rushing out of a compressed air duster to freeze on contact. The technical term is adiabatic cooling, when a gas expands without exchanging heat with its surroundings. The particles spread out, their average kinetic energy drops, and the temperature plummets. The faster the expansion, the more dramatic the cooling. In the Boomerang Nebula, this process occurs on an almost incomprehensible scale. Gas races outward at 101 miles per second, expanding so rapidly that it bleeds away thermal energy faster than any source can replenish it. The material cools as it expands, dropping from the thousands of degrees typical of stellar atmospheres to temperatures that make interstellar space look toasty by comparison. The result? A temperature of approximately 1 Kelvin. That's negative 458 degrees Fahrenheit, negative 272 degrees Celsius, just a single degree above absolute zero. To appreciate how cold this is, consider the baseline temperature of the universe itself. After the Big Bang, the cosmos has been expanding and cooling for nearly 14 billion years. That ancient explosion left behind a faint glow of thermal radiation that fills all of space, the cosmic microwave background. This primordial heat has been stretched and cooled by the universe's expansion. Until today, it registers at 2.7 Kelvin, or about negative 455 degrees Fahrenheit. This cosmic microwave background represents the natural temperature of empty space, the ambient cold that pervades the universe. Everything in the cosmos, unless actively heated by stars or other energy sources, will eventually cool down to match this background temperature. It's the thermal equilibrium of existence itself. But the Boomerang Nebula is colder than this universal baseline. It's the only natural object ever discovered with a temperature below the cosmic microwave background. Think about that. This nebula is colder than the vacuum of space, colder than the farthest reaches between galaxies, colder than the universe itself wants to be. How is that even possible? The cosmic microwave background bathes everything in its faint warmth. constantly depositing tiny amounts of energy into any object cooler than 2.7 Kelvin. For the Boomerang Nebula to maintain temperatures below this background level, it must be cooling itself faster than the universe can heat it back up. The expansion must be so violent, so rapid, that it overwhelms the steady influx of microwave radiation from all directions. This isn't just cold, it's actively, aggressively, impossibly cold. When astronomers Raghvendra Sahai and Lars-Åke Nyman first measured this temperature in 1995, using the Swedish ESO sub-millimeter telescope in Chile, the scientific community was stunned. They discovered something that shouldn't exist according to conventional understanding of how dying stars behave. The measurement was so unexpected that it needed confirmation. In 2013, astronomers used the Atacama Large Millimeter/Sub-Millimeter Array, a collection of 66 radio telescopes in the Chilean desert, to verify the findings. ALMA's observations confirmed it. The Boomerang Nebula really is that cold. But confirmation only deepened the mystery. A dying star, even one shedding mass rapidly, shouldn't be able to create these conditions. The numbers didn't add up. The physics didn't make sense. Something else had to be going on. For years, scientists proposed various explanations. Perhaps the star had an unusually dense stellar wind. Maybe there was some exotic cooling mechanism at work, some unknown process that enhanced the temperature drop. But none of these ideas fully explained the observations. Then, in 2017, Sahai published a study in the Astrophysical Journal that finally provided an answer, and it was more dramatic than anyone had imagined. The Boomerang Nebula isn't the product of a single dying star. It's the aftermath of a cosmic collision, the frozen remnant of stellar cannibalism. The evidence pointed to a binary system, two stars orbiting each other. As the larger star expanded into a red giant, it grew so massive that its outer layers began to interact with its smaller companion. Over time, the gravitational dance between the two stars became unstable. The companion spiraled inward, falling through the outer envelope of the red giant until it plunged directly into the larger star's core. This wasn't a gentle merger. It was a catastrophic collision that released enormous amounts of gravitational energy. The impact ejected most of the red giant's envelope into space in a single violent event, creating the ultra-fast winds we observe today. Only this kind of binary interaction could explain the extreme velocities and massive outflows. A single star, no matter how unusual, simply can't generate the forces necessary to create the Boomerang Nebula's conditions. It required two stars, locked in a fatal embrace, with one sacrificing itself to create the coldest known region in the universe. The nebula's shape provides additional evidence for this theory. When astronomers Keith Taylor and Mike Scarrett first observed it in 1980 using ground-based telescopes, they noticed a distinctive curved structure that reminded them of a boomerang, giving the nebula its name. Later observations with the Hubble Space Telescope revealed much more detail, showing a complex bow-tie shape that would more accurately be described as an hourglass or butterfly pattern. This geometry isn't random. The shape reflects the dynamics of the binary merger, the way material was ejected preferentially along certain directions as the companion star spiraled into the red giant's core. The nebula is essentially a snapshot of cosmic violence, frozen in time and space, preserved at temperatures that barely allow molecular motion. Understanding the Boomerang Nebula requires us to confront a fundamental question about temperature itself. What does it mean for something to be cold? We experience cold as the absence of heat, but that's not quite right. Cold is the absence of thermal energy, the slowing down of particles, the approach toward that quantum limit where motion nearly stops. In everyday life, we never encounter temperatures anywhere near absolute zero. The coldest natural temperature ever recorded on Earth was negative 128.6 degrees Fahrenheit at Antarctica's Vostok Station. That sounds extreme, but on the Kelvin scale, it's still a balmy 184 Kelvin, nowhere close to the cosmic cold of the Boomerang Nebula. Even the coldest places in our solar system are tropical by comparison. Uranus, despite being closer to the Sun than Neptune, holds the record for coldest planetary temperature at 49 Kelvin, or negative 371 degrees Fahrenheit. That's cold enough to freeze carbon dioxide and methane into solid ice, but it's still nearly 50 times warmer than the Boomerang Nebula. The only places that approach such extreme cold are human-made, laboratories where scientists deliberately push the boundaries of how low temperature can go. And these experiments reveal something fascinating about the nature of cold itself. Getting close to absolute zero requires increasingly sophisticated techniques. You can't just stick something in a really good freezer. Normal refrigeration uses compression and expansion of gases, but that approach has limits. To reach the extreme cold needed for cutting-edge physics research, scientists have developed methods that sound like science fiction. One technique is laser cooling, where carefully tuned laser beams slow down atoms by exploiting the Doppler effect. When an atom absorbs a photon moving in the opposite direction to the atom's motion, the atom slows down slightly. By hitting atoms with lasers from multiple directions, scientists can reduce their motion to a crawl, cooling clouds of hundreds of millions of atoms to temperatures around 100 microkelvin, just 1/10,000th of a degree above absolute zero. Another approach uses magnetic fields. Certain atoms behave like tiny magnets, and their orientation affects their energy state. By carefully manipulating magnetic fields, scientists can remove energy from atoms in a process called adiabatic demagnetization, pushing temperatures even lower. The current record for coldest temperature ever achieved in a laboratory was set by German researchers at the University of Bremen in 2021. They cooled a cloud of rubidium atoms to just 38 trillionths of a degree above absolute zero. Let that sink in. 38 trillionths of a degree. That's 38 picokelvin, or 0.00000000000038 Kelvin. At this temperature, atoms move so slowly that quantum effects dominate their behavior completely. Matter itself begins to act in ways that seem to violate common sense, entering exotic states that can't exist at any higher temperature. To achieve this record, the team used a clever trick involving gravity. They created a Bose-Einstein condensate, a quantum state where atoms behave as a single entity, and dropped it down a 120-meter tower. While manipulating magnetic fields during the fall, the free fall environment eliminated gravitational effects on the atoms, allowing the researchers to cool them to temperatures impossible under normal conditions. But here's the fascinating part. Even this record-breaking achievement, the coldest temperature ever created by humans using our most advanced technology in carefully controlled laboratory conditions, is still warmer than the natural cold of the Boomerang Nebula. a cloud of gas 5,000 light-years away, shaped by nothing more than the violent death throes of colliding stars, achieves temperatures that our most sophisticated laboratories can barely approach. Nature, through pure physics and cosmic catastrophe, has created a refrigerator more powerful than anything humanity can build. This raises profound questions about the limits of cold and the nature of temperature itself. How much colder could something get? Is the Boomerang Nebula as cold as nature can achieve? Or might there be even more extreme environments lurking somewhere in the cosmos? To answer these questions, we need to understand what happens as matter approaches absolute zero, how the quantum world begins to dominate, and why scientists are so obsessed with creating and studying these extreme conditions. The journey into the realm of ultimate cold reveals not just the limits of temperature, but the fundamental nature of reality itself. What makes absolute zero so fundamentally unreachable isn't just an engineering challenge, it's written into the laws of physics themselves. The third law of thermodynamics states that no finite process can reduce the temperature of a system to absolute zero. You can get closer and closer, but you'll never quite touch it. Every time you remove energy from a system, the next step becomes exponentially harder. It's like trying to walk to a destination where each step forward must be exactly half the distance of the previous step. You'll get arbitrarily close, but you'll never actually arrive. But here's what makes this truly fascinating. Even if we somehow reached absolute zero, atoms wouldn't completely stop moving. They'd still possess what physicists call zero-point energy, a quantum mechanical phenomenon that prevents particles from ever being truly motionless. The Heisenberg uncertainty principle demands this. If we knew an atom's position with perfect precision, we'd know nothing about its momentum. If we knew its momentum exactly, its position would be completely uncertain. This fundamental quantum fuzziness ensures that even at the coldest possible temperature, particles retain a minimum amount of motion. Zero-point energy isn't just theoretical, it has measurable consequences. The vacuum of space isn't actually empty, it's seething with virtual particles that pop into existence and vanish again in timeframes so brief they don't violate conservation of energy. This quantum foam exists because of zero-point energy, because even empty space can't be perfectly still. Some physicists think this quantum vacuum energy might even explain dark energy, the mysterious force accelerating the universe's expansion. The coldest possible state of matter connects directly to the largest scale structure of the cosmos. So why do scientists obsess over reaching temperatures just trillionths of a degree away from this unreachable limit? Because strange things happen when matter gets that cold. At everyday temperatures, atoms behave like individuals. Each one moves independently, colliding with neighbors in chaotic thermal motion. But as temperature drops, quantum effects that normally remain hidden begin to dominate. Atoms start to lose their individuality. Their quantum wave functions begin to overlap. And at temperatures approaching absolute zero, something extraordinary occurs. In 1995, scientists Eric Cornell and Carl Wieman achieved what had been predicted 70 years earlier, but never observed. They created the first Bose-Einstein condensate, a state of matter so strange it seems to violate common sense. At temperatures below 1/1,000,000th of a degree above absolute zero, a cloud of rubidium atoms transformed. the atoms stopped behaving as separate particles and merged into a single quantum entity. Thousands of atoms acting as one coherent quantum wave. Imagine a stadium full of people all moving randomly. Now imagine cooling that stadium until everyone moves in perfect synchronization, like a single organism. That's what happens in a Bose-Einstein condensate. Matter itself becomes quantum mechanical at a scale we can see. The properties of this state are bizarre. Shine light through a Bose-Einstein condensate and it slows to a crawl. In 1999, physicist Lena Howe reduced light speed to just 17 meters per second, slower than a bicycle. She later stopped light completely, storing it inside the condensate, then released it unchanged. The photons that entered were the same photons that emerged, as if time had paused for them. Bose-Einstein condensates also exhibit superfluidity. Pour liquid helium into a container and cool it to just above absolute zero. It climbs up the walls and flows out, defying gravity. It flows through impossibly tiny gaps without any friction whatsoever. A superfluid forms vortices that never decay, spinning indefinitely with zero energy loss. These aren't magic tricks. They're consequences of quantum mechanics becoming visible at macroscopic scales. But there's another state of matter that emerges from extreme cold, one with even more practical implications. Superconductivity. Certain materials, when cooled below a critical temperature, lose all electrical resistance. Completely. Run a current through a superconducting loop, and it will flow forever without losing energy. The electrons form pairs that move through the material's crystal lattice without scattering, without generating heat, without any of the resistance that plagues normal electrical conductors. The implications are staggering. Superconducting magnets can generate magnetic fields thousands of times stronger than ordinary electromagnets while consuming minimal power. The Large Hadron Collider, the particle accelerator that discovered the Higgs boson, relies on superconducting magnets cooled to 1.9 Kelvin, colder than outer space. MRI machines use superconductors. Experimental maglev trains float on superconducting magnetic cushions. Quantum computers require superconducting circuits to maintain the delicate quantum states that enable their computational power. The challenge with superconductivity has always been the cold. Most superconductors only work at temperatures requiring expensive liquid helium cooling. But in recent decades, physicists discovered high-temperature superconductors, materials that superconduct at temperatures achievable with cheaper liquid nitrogen. The record currently stands at around 250 Kelvin, achieved under extreme pressure. Still cold by everyday standards, but a massive improvement. Some physicists dream of room-temperature superconductors, materials that could revolutionize power transmission, transportation, and computing. We're not there yet, but we're learning. These exotic states of matter reveal something profound about temperature itself. We think of hot and cold as opposite ends of a spectrum, but that's not quite right. Heat is energy. Cold is the absence of energy. There's no limit to how hot something can be. The center of a massive star reaches billions of degrees. Particle collisions can briefly create temperatures trillions of degrees, conditions that last existed microseconds after the Big Bang. But cold has a hard limit. You can't have less than zero energy. This asymmetry shapes the universe. In the beginning, everything was unimaginably hot. The Big Bang started with infinite temperature compressed into an infinitesimal point. As space expanded, it cooled, particles formed, forces separated, matter condensed, stars ignited, and through it all, the universe has been cooling, radiating energy into an ever larger volume of space. Today, the baseline temperature of the universe is 2.7 Kelvin, the temperature of the cosmic microwave background radiation left over from the Big Bang. This is the temperature of empty space itself, the thermal afterglow of creation, and it's still cooling. As the universe expands, this background radiation gets stretched to longer wavelengths, lower energies, colder temperatures. In the far future, trillions of years from now, the universe will approach a state called heat death. All stars will have burned out. Black holes will have evaporated. The temperature everywhere will asymptotically approach absolute zero. The universe won't quite reach it. Quantum effects will prevent that, but it will get arbitrarily close. The cosmos will become a cold, dark, nearly motionless expanse where nothing interesting can ever happen again. But we're nowhere near that fate yet. And in the meantime, scientists continue pushing the boundaries of cold, creating conditions in laboratories that don't naturally exist anywhere in the universe. Well, almost anywhere. Remember the Boomerang Nebula? That cosmic exception sitting at 1 degree Kelvin, colder than the space around it, colder than the background radiation that permeates everything. How does nature achieve what our most advanced laboratories struggle to match? The answer lies in expansion. Rapidly expanding gas cools. This is the same principle behind your refrigerator, behind aerosol cans that feel cold when sprayed, behind the Bremen drop tower experiment that set the laboratory cold record. When gas expands, its molecules spread out, moving farther apart. The energy that was concentrated in a small volume gets distributed across a larger volume. Temperature drops. But the Boomerang Nebula takes this to an extreme. The dying star at its center is expelling gas at 164 kilometers per second, 500,000 kilometers per hour. That's 0.05% the speed of light. This isn't a gentle stellar wind. It's a catastrophic ejection event, blasting away 1,000th of a solar mass per year. Over 1,500 years, the star has lost 1.5 times the mass of our Sun. This extraordinary mass loss remained a mystery for decades. Single stars don't behave this way. Even dying red giants, stars in their final evolutionary stages shedding outer layers, lose mass far more gradually. The Boomerang Nebula was an outlier, an anomaly that didn't fit our understanding of stellar death. Then, in 2017, astronomer Raghvendra Sahai published new observations from ALMA, the Atacama Large Millimeter Array in Chile. The data revealed something unexpected. The nebula's structure suggested not one star dying, but two stars interacting. The Boomerang Nebula likely formed when a smaller companion star spiraled into the heart of a larger red giant in a cosmic death plunge. When two stars merge, the gravitational energy released is enormous. This energy blasted the red giant's outer layers into space at velocities far beyond what a single dying star could achieve. The ultra-rapid expansion created the ultra-cold temperatures. The collision literally froze the ejected gas, creating nature's most powerful refrigerator through one of the universe's most violent events. This binary interaction explains everything. The extreme cold, the rapid expansion, the unusual structure. Two stars dying together created conditions that a single star never could. And somewhere in that cloud of freezing gas, hidden at the nebula's heart, The remnants of those stars still orbit each other, their collision creating the coldest natural environment we've ever found. But this raises a question. Could there be places even colder? Could other stellar catastrophes create even more extreme cooling? Or has the Boomerang Nebula hit some natural limit, some cosmic boundary beyond which matter simply cannot be cooled by natural processes? The answer requires understanding how cold connects to the quantum world, how temperature shapes the very fabric of reality, and why the coldest places in the universe reveal the deepest truths about how nature operates at its most fundamental level. The universe doesn't simply get colder by accident. Temperature is energy. When particles move faster, collide more frequently, vibrate with greater intensity, we call that heat. When they slow down, spreading apart, losing that kinetic frenzy, we call that cold. But what happens when you remove almost all the energy? When particles barely move at all? You enter a realm where the rules change completely. Quantum mechanics takes over. At everyday temperatures, quantum effects are invisible. The thermal noise, the constant jittering of atoms, drowns out quantum behavior like static overwhelming a whisper. But approach absolute zero, and that noise fades. The whisper becomes audible. Particles start behaving in ways that seem impossible, following rules that contradict everything our senses tell us about how matter should work. Consider this. In 1924, Indian physicist Satyendra Nath Bose sent Einstein a paper describing a new way to think about photons. Einstein extended the idea to atoms. Together they predicted something extraordinary. Cool certain atoms to temperatures near absolute zero, and they would stop behaving as individuals. They would merge into a single quantum entity, a superatom, where thousands of particles occupy the same quantum state, moving in perfect synchronization. Nobody believed it would actually happen. For 70 years, the Bose-Einstein condensate remained theoretical, a mathematical curiosity that seemed too bizarre to exist in reality. Then in 1995, researchers at MIT and the University of Colorado independently created one. They cooled rubidium and sodium atoms to billionths of a degree above absolute zero. And the atoms did exactly what Bose and Einstein predicted. They became one. In a Bose-Einstein condensate, individual atoms lose their identity. Their quantum wave functions overlap, merging into a single coherent quantum state. Shine light through this condensate and strange things happen. The light slows down, way down. Scientists have reduced light's speed from 300 million meters per second to just 17 meters per second in a BEC. Light moving slower than a commercial jet. In 2001, researchers at Harvard actually stopped light completely, froze it inside a condensate, then released it again. The light picked up exactly where it left off, as if time itself had paused. This isn't science fiction. This is what matter does when you remove almost all its thermal energy. But creating these conditions requires extreme cold, temperatures that dwarf even the Boomerang Nebula's 1 degree Kelvin. The coldest BECs exist at temperatures measured in billionths or even trillionths of a degree above absolute zero. Nature's coldest place is a tropical paradise compared to these laboratory environments. The question emerges naturally: how cold can we go? Is there a practical limit beyond which no technique, no technology can push us closer to absolute zero? The third law of thermodynamics says yes. Reaching absolute zero would require infinite steps, infinite time, infinite energy. It's not just difficult, It's physically impossible, but that hasn't stopped physicists from trying to get as close as possible. Each new record reveals something unexpected about how matter behaves at the edge of existence. The current champion is a German team that achieved 38 trillionths of a degree above absolute zero, not in a conventional laboratory, but in a drop tower. They created a Bose-Einstein condensate from 100,000 rubidium atoms, trapped it in a magnetic field, then dropped the entire apparatus 120 meters down a tower. During the 2-second fall, gravity effectively disappeared. In that microgravity environment, the magnetic field could be switched on and off rapidly, causing the condensate to expand and contract. Each cycle removed more thermal energy. The gas cooled to temperatures that would be impossible to maintain under normal gravity. Why does microgravity help? Gravity pulls atoms downward, compressing clouds of ultra-cold gas, heating them through that compression. Remove gravity, and the gas can expand without that interference. The atoms spread out more freely. Temperature drops further. The experiment lasted only 2 seconds, but those 2 seconds were enough to set a record that still stands. Simulations suggest that in a true weightless environment, like aboard a satellite, these temperatures could be maintained for 17 seconds. Long enough to study quantum phenomena that occur on timescales too brief to observe on Earth. Long enough to see quantum mechanics in action without gravity interfering. But why pursue such extreme cold? What can we learn at 38 trillionths of a degree that we can't learn at, say, 38 millionths of a degree? The answer lies in what temperature actually measures. We think of temperature as hot or cold, but fundamentally it measures disorder, chaos, the random motion of particles. High temperature means high disorder, particles moving in random directions, colliding unpredictably, creating noise that obscures patterns. Low temperature means low disorder, particles settling into organized states, quantum patterns emerging from the chaos like constellations, appearing as city lights fade. At ultra-low temperatures, quantum mechanics becomes the dominant force governing matter. Particles no longer behave like tiny billiard balls following classical physics. They behave like waves, interfering with each other, creating patterns of probability rather than definite trajectories. Quantum entanglement becomes observable on scales large enough to see. Superfluidity emerges, where liquids flow without friction, climbing up and over container walls as if gravity didn't exist. Superconductivity appears, where electrical resistance drops to exactly zero. Electrons pair up and move through materials as a single quantum entity, carrying current without losing energy. This quantum pairing only happens at low temperatures. Too much thermal energy and the pairs break apart. The resistance returns. The magic disappears. These phenomena aren't just laboratory curiosities. They're the foundation of emerging technologies. Quantum computers require temperatures in the millikelvin range, thousandths of a degree above absolute zero to function. At these temperatures, quantum bits can maintain their delicate superposition states long enough to perform calculations. Warm them up even slightly, and those superpositions collapse. The quantum information vanishes before the calculation completes. This is why companies like IBM and Google maintain dilution refrigerators, specialized cooling systems that use quantum properties of helium isotopes to reach temperatures below 10 millikelvin. These refrigerators cost millions of dollars and require constant maintenance. They're among the most sophisticated cooling devices ever built, yet they're essential for quantum computing to work. The Colossus dilution refrigerator under construction at Fermilab takes this to another level entirely. When completed in 2025, it will cool over 5 cubic meters of space to around 10 millikelvin. That's 15 times larger than typical dilution refrigerators. The scale isn't just impressive, it's necessary. As quantum computers grow from laboratory prototypes to practical devices, they need more space at ultra-low temperatures, more qubits, more quantum processors, more room for the quantum operations that might revolutionize computing. But maintaining such large volumes at such low temperatures presents engineering challenges that border on the absurd. Every surface radiates heat. Every wire conducting electricity generates thermal energy. Every measurement introduces warmth. The refrigerator must remove all this heat continuously while maintaining temperatures where the difference between 1 millikelvin and 2 millikelvin matters enormously. Compare this to the Cuori experiment in Italy, which holds a different kind of record. Cuori cooled a cubic meter of copper, weighing 400 kilograms, to just 0.006 of a degree above absolute zero. Not as cold as the German team's rubidium atoms, but far more massive. Cooling such a large solid object to these temperatures required weeks of continuous operation. The copper had to be extraordinarily pure. Any impurities would trap heat, preventing the temperature from dropping further. Cuori wasn't built to set records. It was built to detect rare particle interactions, events so subtle that thermal noise would completely obscure them at higher temperatures. Only at temperatures within a few thousandths of a degree of absolute zero could the detectors achieve the sensitivity needed to see these quantum events. This reveals something profound about cold. It's not just about reaching low temperatures. It's about creating conditions where quantum mechanics dominates, where the underlying reality of the universe becomes visible. At room temperature, roughly 300 Kelvin, quantum effects are everywhere but invisible. The atoms in your body constantly exchange quantum information with each other, but that information is scrambled by thermal motion faster than it can be measured. Cool those same atoms to microkelvin temperatures, and suddenly quantum coherence lasts long enough to observe. The atoms remember their quantum states. They maintain entanglement. They behave not as individuals, but as quantum systems, following rules that seem to violate common sense. Wolfgang Ketterle's team at MIT demonstrated this dramatically in 1995, when they created the first Bose-Einstein condensate of sodium atoms. They cooled the atoms to 0.5 billionth of a degree above absolute zero. At that temperature, the atoms underwent a phase transition unlike anything in everyday experience. They didn't freeze into a solid. They didn't condense into a liquid. They transformed into something entirely different, a quantum gas, where all the atoms occupied the same quantum state simultaneously. Shine a light on a normal gas, and each atom interacts with the light independently. Shine a light on a BEC, and the entire condensate responds as one. The atoms move together, absorb photons together, emit radiation together. It's as if 100,000 individual instruments suddenly started playing in perfect unison without a conductor. This quantum coherence enabled experiments that seemed impossible. Researchers created atom lasers, beams of atoms that travel in perfectly synchronized quantum waves. They generated quantum vortices, tornadoes of quantum matter spinning with quantized angular momentum. They observed matter wave interference patterns, where atoms interfere with themselves like waves on water. All of this requires cold. Not just cold, but cold beyond anything nature produces on its own. The Boomerang Nebula's 1 degree Kelvin is impressive for a natural object, but it's still too warm for these quantum phenomena to appear. The thermal energy at 1 degree Kelvin is still enough to disrupt quantum coherence, to keep atoms behaving classically rather than quantum mechanically. This creates an interesting paradox. The coldest natural place in the universe isn't cold enough to reveal nature's deepest quantum secrets. We have to create conditions colder than anywhere in the cosmos to see how the universe truly works at its most fundamental level. Yet, there's a limit. Not a practical limit, a theoretical one. Absolute zero, 0 Kelvin, negative 273.15 degrees Celsius, represents more than just the absence of heat. It represents a boundary written into the laws of physics. At absolute zero, classical motion stops. Atoms would sit perfectly still. But quantum mechanics forbids this. The Heisenberg uncertainty principle states that we cannot know both an atom's position and momentum with perfect precision. If an atom were truly at rest, we would know its momentum exactly, 0. That would require infinite uncertainty in its position, meaning the atom could be anywhere. This is impossible. The atom must retain some motion, some residual quantum jitter called zero-point energy. Even at absolute zero, quantum motion persists. Atoms vibrate with their minimum quantum mechanical energy, not because they're warm, but because quantum mechanics demands it. This zero-point energy is why helium remains liquid even at absolute zero under normal pressure. The quantum vibrations prevent the atoms from settling into a solid crystal. Only under enormous pressure does helium finally solidify. This quantum limit means absolute zero isn't just hard to reach, it's unreachable in principle. Every quantum system retains some energy, some motion, some uncertainty. Remove all the thermal energy you want, the quantum energy remains. And measuring these extreme temperatures becomes its own challenge. At 38 trillionths of a degree above absolute zero, how do you even know what temperature you've achieved? Thermometers don't work. Contact with a measuring device would heat the system. You have to infer temperature from indirect measurements, from the behavior of atoms, from quantum states and energy distributions. The measurement itself has uncertainty. At such extreme cold, distinguishing between absolute zero and 38 trillionths of a degree requires measurement precision that pushes the limits of what's physically possible. This raises a question that connects back to the cosmic cold of the Boomerang Nebula. If laboratory conditions can reach temperatures trillions of times colder than nature's coldest place, does that mean we've surpassed the universe itself? Have we created something more extreme than anything cosmic processes can achieve? In a strange way, yes. We've engineered conditions more extreme than stellar death, more extreme than the aftermath of cosmic explosions, more extreme than anything occurring naturally anywhere in the observable universe. This tells us something profound about intelligence and technology. Nature, left to its own devices, can create remarkable extremes. Stellar cores reach millions of degrees. Neutron stars compress matter to nuclear density. The Boomerang Nebula achieves temperatures below the cosmic background radiation through violent expansion. But deliberate control beats random chance. Every time, The Boomerang Nebula reached 1 degree Kelvin through catastrophic stellar death. Two stars merging, ejecting matter at 500,000 kilometers per hour, creating conditions so violent they overwhelm the ambient heat of space itself. It's spectacular, it's extreme, but it's also essentially a cosmic accident. Human-made cold, on the other hand, represents controlled precision. Lasers tuned to exact frequencies, magnetic fields switched on and off with nanosecond timing, atoms manipulated one by one into specific quantum states. We don't match nature's violence. We exceed it through careful orchestration. This pattern appears throughout science. Nature creates diamonds through geological pressure over millions of years. We create them in laboratories in hours. Nature produces elements up to uranium through stellar nucleosynthesis. We create heavier elements in particle accelerators. Nature evolved flight through millions of years of selection. We engineered it in a decade. Intelligence allows shortcuts. Understanding lets us compress billions of years of natural processes into controlled experiments lasting seconds. But there's something else happening in these ultra-cold laboratories. Something that reveals why scientists care about temperatures trillions of times colder than the coldest cosmic nebula. Temperature is energy. Lower temperature means less energy, less random motion, less noise obscuring what's really happening at fundamental levels. Think of trying to observe a small, delicate pattern on a table. If the table's shaking violently, you can't see the details. The vibration overwhelms everything else. Most matter exists on violently shaking tables. Room temperature means atoms jiggling with energies far larger than the subtle quantum effects physicists want to study. Even the Boomerang Nebula at 1 degree Kelvin has too much thermal noise for many quantum phenomena. Only at temperatures measured in millionths or billionths of degrees does the shaking stop enough for quantum mechanics to dominate completely. Then the universe reveals its true strangeness. Superconductivity emerges. Certain materials suddenly conduct electricity with zero resistance, no energy loss, perfect efficiency. This doesn't happen at room temperature. The thermal vibrations disrupt the delicate quantum coordination between electrons that makes superconductivity possible. Cool these materials down, remove the thermal noise, and suddenly electrons pair up in quantum lockstep. They flow through the material as a unified quantum wave, impervious to the atomic obstacles that normally create resistance. The material becomes a perfect conductor. This isn't just scientifically interesting, it's technologically revolutionary. Superconducting magnets make MRI machines possible. Superconducting cables could transmit power across continents without loss. Superconducting quantum computers promise computational capabilities beyond anything classical systems can achieve. None of it works at room temperature. All of it requires cold that surpasses anything natural. Superfluidity appears too. Cool helium below about 2 degrees. Kelvin and it transforms into something that defies everyday physics. It climbs up and over the walls of containers. It flows without friction. It forms quantum vortices that persist indefinitely. This happens because the helium atoms enter a single quantum state. They stop behaving like individual particles and start acting as one unified quantum system. The distinction between separate atoms blurs. The fluid becomes a macroscopic quantum object, governed by the same rules that govern individual particles. You can't see this at higher temperatures. Thermal energy keeps atoms behaving classically. like tiny billiard balls bouncing around. Only extreme cold removes enough energy for quantum behavior to dominate on scales visible to the human eye. Then there's the precision measurement capabilities unlocked by ultra-cold systems. Atomic clocks, the most accurate timekeeping devices ever created, rely on laser-cooled atoms. By removing thermal motion, these clocks measure time with precision beyond 1 second in 300 million years. That's not just impressive, it's practically useful. GPS systems depend on precise timing. Relativity means satellites experience time differently than ground stations. Without accounting for these tiny differences, GPS would drift by kilometers per day. Atomic clocks make GPS possible, and atomic clocks require temperatures far below anything the Boomerang Nebula achieves. Quantum computers represent perhaps the most ambitious application. These machines exploit quantum superposition, where quantum bits exist in multiple states simultaneously until measured. This allows certain calculations to be performed exponentially faster than any classical computer. But quantum superposition is fragile. Thermal energy destroys it. Stray vibrations collapse the quantum states. To maintain quantum coherence long enough for computation requires cooling to millikelvin temperatures, thousandths of a degree above absolute zero. This is why Fermilab is building Colossus, a dilution refrigerator larger than any previously constructed. 5 cubic meters of space cooled to 10 millikelvin. Room for thousands of quantum devices. Infrastructure for quantum computers that might eventually revolutionize cryptography, drug discovery, materials science, artificial intelligence. None of it possible at the Boomerang Nebula's temperature. All of it requiring human-engineered cold that nature never produces. Here's what's remarkable about this progression. Each advance in cooling technology opened new physics. Each time scientists thought they'd reached practical limits, new techniques emerged. In the 1990s, laser cooling seemed like the ultimate achievement, cooling atoms to microkelvin temperatures by essentially hitting them with photons until they slowed down. Nobel Prize-winning work, but laser cooling has limits. Eventually, atoms stop absorbing photons efficiently. The technique plateaus around 1 microkelvin. Then came evaporative cooling, borrowed from how coffee cools. Remove the hottest atoms from a trapped cloud, and the average temperature drops. This pushed temperatures down to nanokelvin, billionths of a degree. The Bremen Drop Tower experiment combined evaporative cooling with microgravity. By dropping the apparatus, they eliminated gravitational disturbances that normally heat the atoms. Result: 38 trillionths of a degree, closer to absolute zero than any previous measurement. Each technique builds on previous ones. Each generation of physicists finds new ways to remove energy, to quiet the quantum system, to see deeper into how reality works at its foundation. And we're not done. Simulations suggest the drop tower technique could maintain these temperatures for 17 seconds in true weightlessness on a satellite. Space-based cold atom experiments might reach even lower temperatures. There's talk of cooling not just small clouds of atoms, but larger systems, cooling molecules instead of atoms, cooling mechanical oscillators into their quantum ground state. Each advance reveals new physics, new possibilities, new technologies. But let's return to the comparison with the Boomerang Nebula. What does it mean that we've created conditions more extreme than stellar death? It means intelligence and understanding trump brute force. The nebula achieved its temperature through violence, through the merger of two stars and catastrophic mass ejection. Overwhelming power creating extreme conditions as a byproduct. We achieve lower temperatures through precision, through understanding exactly which quantum transitions remove energy most efficiently, through engineering magnetic fields that trap atoms without heating them, through timing laser pulses to nanosecond accuracy. This pattern reveals something about how progress works. Early achievements often require enormous resources. The first atomic clocks filled entire rooms. The first computers occupied buildings. The first particle accelerators barely achieved energies now surpassed by tabletop devices. Then understanding deepens. Techniques refine. What once required massive scale becomes achievable with precision and cleverness. The Boomerang Nebula represents nature's massive scale approach to cold. Stellar mass ejection at 500,000 kilometers per hour. Violence and power creating 1 degree Kelvin. The Bremen Drop Tower represents humanity's precision approach. 100,000 atoms in a magnetic trap. Careful manipulation achieving 38 trillionths of a degree. Both reach extreme cold, but only one approach scales toward practical applications. Only one can be controlled, repeated, refined. Only one can be engineered into devices that fit in laboratories rather than requiring stellar death. This is why those 38 trillionths of a degree matter. Not because cold is inherently valuable, but because it's a tool. A tool for seeing quantum mechanics in action. A tool for building quantum computers. A tool for measuring time with unprecedented precision. A tool for understanding how the universe works at its deepest level. The Boomerang Nebula will eventually warm. Its violent expansion will slow. The ejected gas will dissipate. Cosmic microwave background radiation will gradually heat it above its current record-breaking cold. In cosmological terms, this moment of extreme cold is temporary. But human-made cold persists. Every time a dilution refrigerator cools, it creates conditions colder than the nebula. Every time a laser cooling experiment runs, it surpasses stellar death's cooling power. The capability doesn't depend on rare cosmic events. It depends on understanding and technology. That understanding keeps advancing. The Italian Cuori experiment cooled 400 kilograms of copper to 6/1000ths of a degree above absolute zero. That's not as cold as the atomic gas experiments, but it's remarkable for a different reason. Cooling that much mass to that temperature requires solving enormous engineering challenges. Cuori exists to detect neutrinos, ghostly particles that barely interact with matter. To see these rare interactions requires eliminating thermal noise that'd overwhelm the signal. Hence the extreme cold, maintained for over 15 days in a cubic meter of space. This demonstrates another aspect of ultra-cold technology: duration and stability. The Bremen experiment achieved lower temperature, but only for 2 seconds. Cuori achieved slightly warmer temperature, but maintained it for weeks in a much larger volume. Different experiments require different capabilities. Quantum computing needs small systems extremely cold. Particle physics needs large systems moderately cold. Materials science needs sustained cold to study long-term quantum behavior. We're developing the full toolkit, not just how to reach extreme cold, but how to maintain it, how to scale it, how to use it for specific applications. This brings us back to the question of measurement. How do we know the Bremen experiment reached 38 trillionths of a degree? You can't stick a thermometer in. contact would heat the system. Instead, temperature is inferred from quantum states, from the velocity distribution of atoms, from the width of spectral lines, from how the system responds to tiny perturbations. Each measurement has uncertainty. At 38 trillionths of a degree, that uncertainty becomes comparable to the temperature itself. We're measuring something so close to absolute zero that quantum uncertainty makes the very concept of temperature slightly fuzzy. This isn't a flaw in our instruments, it's a fundamental limit. Temperature measures average kinetic energy, but quantum mechanics limits how precisely we can know both position and momentum. At extreme cold, quantum uncertainty becomes the dominant factor. We're pushing measurement to where classical concepts like temperature start breaking down, where quantum mechanics forces us to rethink what we mean by heat, energy, motion itself. That's the real significance of these ultra-cold experiments. Not just that we've beaten the Boomerang Nebula, but that we're exploring the boundary where classical physics gives way to quantum mechanics completely, where the universe reveals its fundamental strangeness. And what we find there shapes technology for decades to come. Quantum computers already operate in dilution refrigerators. Google's Sycamore processor, IBM's quantum systems. Every major quantum computing effort requires these machines. The qubits storing quantum information are superconducting circuits, electrical currents flowing without resistance, but superconductivity only exists below critical temperatures. For most materials used in quantum computing, that's around 10 millikelvin. Thermal energy at room temperature would destroy quantum states instantly. Even at liquid helium temperature, 4 Kelvin, there's too much noise. The qubits need protection from thermal fluctuations that would collapse their delicate superposition states. Dilution refrigerators provide that protection. Multiple cooling stages cascade from room temperature down to base temperature. Outer stages use liquid nitrogen at 77 Kelvin. Inner stages use liquid helium at 4 Kelvin. The final stage exploits helium isotope mixing to reach millikelvin range. This isn't simple refrigeration, it's quantum mechanical heat extraction. Helium-3 and helium-4 behave differently at low temperatures because they're quantum fluids. Below about 1 Kelvin, helium-4 becomes a superfluid, flowing without viscosity, climbing walls, behaving in ways that defy classical physics. Helium-3 is even stranger. It's a fermion, following Pauli exclusion principle. Mix the two isotopes at low temperature and they phase separate like oil and water. But the separation process absorbs heat. Engineers exploit this continuously. Circulating the isotope mixture creates steady, cooling power. The system can maintain millikelvin temperatures indefinitely as long as helium circulates and pumps operate. But why do quantum computers need such extreme cold? The answer reveals something fundamental about information itself. Information is physical. Every bit stored, every calculation performed requires energy. Thermodynamics sets limits on computation based on temperature. The hotter the system, the more energy required per operation. At room temperature, thermal fluctuations swamp quantum effects. Atoms jiggle violently. Electrons scatter randomly. Any quantum state would decohere, lose its quantum properties in femtoseconds. Cool the system and thermal energy decreases. Quantum effects emerge from the noise. At millikelvin temperatures, quantum states can persist for milliseconds. That's 1 billion times longer than at room temperature. Still not long enough for complex calculations. Quantum error correction helps, but fundamentally, the battle is against decoherence, against thermal energy disrupting quantum information. This explains the race toward larger dilution refrigerators. Scaling quantum computers requires cooling more qubits simultaneously. Colossus at Fermilab represents that ambition. 5 cubic meters of cooling volume. Capacity for thousands of qubits. Compare that to typical quantum computers today with dozens or hundreds of qubits. Colossus isn't just incrementally larger. It's orders of magnitude beyond current systems. The construction challenges are extraordinary. Maintaining millikelvin temperatures across 5 cubic meters means eliminating every heat source, radiation from the walls, vibrations from the building, electromagnetic interference from the environment. Each cooling stage must be thermally isolated from warmer stages above while remaining mechanically connected. Each cable carrying signals to the qubits conducts heat that must be managed. Every component must function reliably at cryogenic temperatures, where materials behave unexpectedly. Metals become brittle, plastics shatter, lubricants freeze solid. Normal engineering intuition fails. Yet solving these problems matters beyond quantum computing. Ultra-low temperature physics opens windows into phenomena that don't exist at higher temperatures. Superconductivity, superfluidity, Bose-Einstein condensates. These aren't just laboratory curiosities. They reveal how matter behaves when quantum mechanics dominates completely. Superconductors carry current without resistance. Power lines made from superconducting materials would eliminate transmission losses. Maglev trains float on superconducting magnets. MRI machines use superconducting coils to generate strong magnetic fields. Currently, these applications require liquid helium cooling, expensive and impractical for most uses. But high-temperature superconductors work above liquid nitrogen temperature. Still cold by everyday standards, -196 Celsius, but far more practical than millikelvin systems. Understanding superconductivity requires studying it at the lowest possible temperatures, where quantum effects are strongest and most visible, where theoretical predictions can be tested with precision. The same applies to superfluidity. Liquid helium flows uphill, forms impossible fountains, conducts heat better than any metal. These aren't tricks. They're consequences of quantum mechanics applied to macroscopic amounts of matter. At ultra-low temperatures, thousands or millions of atoms occupy the same quantum state. They move as one entity. Their wave functions overlap completely. Individual identity disappears into collective quantum behavior. This state, Bose-Einstein condensate, was predicted in 1924. Not observed until 1995. The achievement required laser cooling to microkelvin temperatures. Wolfgang Ketteler, Eric Cornell, and Carl Wieman shared the Nobel Prize. Their work opened a new field. Researchers now study BEC properties, create exotic quantum states, explore analogies to cosmology and particle physics using ultra-cold atoms. But creating BEC requires more than low temperature. It requires the right atoms cooled the right way. Laser cooling works through a clever trick. Tune laser frequency slightly below atomic absorption frequency. Atoms moving toward the laser see blue shifted light matching their absorption. They absorb photons, slowing down. Atoms moving away see red shifted light that doesn't match. They don't absorb. Result: atoms selectively absorb, Only when moving toward the laser, momentum transfer opposes their motion. They slow down, temperature drops. Multiple lasers from different directions create optical molasses, atoms trapped in intersecting laser beams, cooled to microkelvin temperatures. But there's a limit. Recoil from absorbing single photons creates a minimum temperature. For sodium atoms, that's about 240 microkelvin. Not cold enough for BEC. The final step uses evaporative cooling. Let the hottest atoms escape. Remaining atoms redistribute energy through collisions. Average energy decreases. Temperature drops. It's like blowing on hot coffee. You remove the fastest moving molecules, cooling what remains. This technique pushed temperatures below 1 nanokelvin in the MIT experiment, low enough for thousands of atoms to condense into a single quantum state. The resulting matter behaves impossibly. Shine light through it and the BEC acts like a single atom. Apply magnetic fields and it responds collectively. Disturb it and quantum waves ripple through the condensate. These aren't small effects, they're macroscopic quantum phenomena, visible demonstrations that quantum mechanics governs everything, not just subatomic particles. Now compare the MIT achievement to the Bremen drop tower. Both reached extreme cold. But Bremen's 38 trillionths of a degree represents a different approach entirely. Instead of laser cooling alone, they combined it with expansion cooling. The BEC starts at 2 billionths of a degree, already extraordinarily cold. Then the magnetic trap releases during free fall. Without gravity's compression, the atomic cloud expands. Expansion means atoms spread out. Kinetic energy converts to potential energy. Temperature drops. But there's a subtlety. Why free fall? Gravity limits how long you can observe expanding BEC on Earth. The atoms fall. The experiment ends. But during free fall in the drop tower, gravity effectively disappears. The atoms float weightless. The expansion continues unimpeded. 2 seconds of free fall. 2 seconds at 38 trillionths of a degree. Then the apparatus hits the bottom and the experiment ends. Why go through this trouble? Because at those temperatures, quantum effects reach maximum strength. Time itself seems to slow for the atoms. Quantum states persist longer. Measurements become more precise. The team's simulations suggest 17 seconds might be possible in space. A satellite carrying the experiment could maintain free fall indefinitely. No drop tower height limit. No impact at the bottom. This points toward future experiments. Cold atom physics in orbit. Quantum sensors free from Earth's vibrations. Tests of fundamental physics where gravity's effects minimize. Already, NASA has operated BEC experiments on the International Space Station. The Cold Atom Laboratory produces condensates in microgravity, studies their properties, develops new quantum technologies. These efforts parallel the ground-based push toward extreme cold. Different approaches toward the same goal. Understanding quantum mechanics at its most fundamental. The Boomerang Nebula achieved its cold through stellar violence. Bremen's experiment through precision engineering and quantum manipulation. Quarry through massive cryogenic infrastructure. Each represents a different path to extreme cold. Yet all share something profound. They push against the same fundamental limit. Absolute zero isn't just a temperature. It's a boundary where classical physics ends and quantum mechanics completely takes over. Temperature measures average kinetic energy. At absolute zero, that average reaches minimum. Not zero exactly, Quantum mechanics forbids that, but the minimum allowed by Heisenberg's uncertainty principle. This zero-point energy persists even at absolute zero. Atoms still vibrate, electrons still orbit, fields still fluctuate, but the energy can't be extracted. It's locked in by quantum mechanics. Think of it as the universe's fundamental jitter, an irreducible quantum restlessness that prevents perfect stillness. This jitter has consequences. Virtual particles pop from vacuum. Empty space has energy density. Cosmological constant might derive from zero-point energy. The universe itself shaped by quantum fluctuations that can't be eliminated. Approaching absolute zero means approaching the realm where these effects dominate, where thermal energy no longer masks quantum behavior, where we see reality's fundamental quantum nature clearly. Every advance in cooling technology brings us closer, from liquid helium to dilution refrigerators, to laser cooling, to expansion cooling in free fall. Each technique extends our reach toward absolute zero, but will never arrive. Thermodynamics forbids it. The third law states no finite process can reach absolute zero in finite steps. You can get arbitrarily close, 38 trillionths of a degree, perhaps someday 38 quadrillionths, but never exactly zero. Why? Because removing the last bit of heat requires infinite work. The system's entropy must reach zero. Perfect order, perfect stillness, impossible in finite time with finite energy. This isn't engineering limitation, it's fundamental physics. The universe protects absolute zero like an asymptote, approachable but unreachable. Yet the pursuit continues, because each incremental advance reveals new physics. Each factor of 10 colder opens new phenomena. Each record broken expands what's possible. Quantum computing needs colder systems for better qubits. Particle physics needs colder detectors for better sensitivity. Fundamental physics needs colder atoms for better measurements. The coldest place in the universe started as an accident of stellar death. Now it's a target, a benchmark to exceed, a challenge driving technology forward, and we've exceeded it. Multiple times, in multiple ways. The Boomerang Nebula's won. Kelvin seems almost warm compared to laboratory achievements. But perhaps that's the wrong comparison. Natural cold versus engineered cold. Cosmic accident versus deliberate creation. Temporary phenomenon versus sustained capability. The nebula will warm. Laboratory cold can be repeated indefinitely. The universe stumbled upon extreme cold once through rare circumstance. Humanity develops the capability systematically through understanding. That's the real achievement. Not beating the nebula's record, but understanding temperature so deeply we can approach absolute zero through multiple independent methods. The coldest place in the universe is now wherever scientists choose to make it. But something else happens as we master extreme cold. Applications emerge that nobody predicted. Quantum computers don't work at room temperature. Qubits, quantum bits, need cold to maintain superposition. Thermal noise destroys quantum states instantly. Every vibration, every stray photon collapses the delicate quantum information. Dilution refrigerators solve this. They exploit quantum mechanics itself to remove heat. Two helium isotopes, helium-3 and helium-4, mixed together in specific ways, create cooling through phase separation. Not compression expansion like your refrigerator. Quantum phase separation. Helium-3 dissolves into helium-4 at ultra-low temperatures. The process absorbs heat. Lots of it. Enough to reach millikelvin temperatures. 5/1000ths of a degree above absolute zero. That's cold enough for superconducting qubits, for quantum processors, for the computers that might revolutionize everything from cryptography to drug discovery. Google's quantum computer sits in a dilution refrigerator. So does IBM's. Every major quantum computing effort depends on technology developed to reach extreme cold. The coldest temperatures humanity can achieve enable computation that's impossible at any higher temperature. Superconductivity emerges at low temperatures too, materials that conduct electricity with zero resistance. No heat loss, no wasted energy, but only below critical temperatures that vary by material. High-temperature superconductors work around 90 Kelvin, still requires liquid nitrogen, still far from room temperature. The dream of room temperature superconductivity remains elusive despite decades of research. But cold-enabled superconductivity already transforms technology. MRI machines use superconducting magnets. Particle accelerators like the Large Hadron Collider depend on superconducting components. Future power grids might transmit electricity without loss using superconducting cables, all enabled by understanding how to reach and maintain extreme cold. Then there's superfluidity. Below 2.17 Kelvin, helium-4 becomes something extraordinary. A superfluid with zero viscosity. It flows without friction. It climbs walls. It leaks through microscopic holes that would stop normal liquids. Superfluid helium defies classical physics completely. It's a macroscopic quantum phenomenon, quantum mechanics operating at scales you can see with your eyes. The entire fluid behaves as a single quantum entity. Scientists still debate aspects of superfluidity, the formation of quantized vortices, the behavior at boundaries, the connection to other quantum phenomena. Ultra-cold experiments continue revealing new physics. Bose-Einstein condensates represent another frontier. When atoms cool below a few billionths of a degree above absolute zero, they enter a new state of matter, not solid, liquid, gas, or plasma, something else entirely. Wolfgang Kettel and others first created Bose-Einstein condensates in 1995 at MIT. They cooled sodium atoms to half a nanokelvin. The atoms lost their individual identities. They merged into a single quantum state, a matter wave described by one wave function. You can manipulate BECs in ways impossible with ordinary matter. Slow light to walking speed, create quantum vortices, study quantum turbulence, simulate other quantum systems. The coldest laboratory temperatures enable all this. Bremann's drop tower experiment achieved 38 trillionths of a degree above absolute zero for 2 seconds. Enough time for measurements, for observations, for advancing fundamental understanding. But why drop them? Gravity interferes with ultra-cold atoms. Earth's gravitational field pulls harder on some parts of the atom cloud than others, creates gradients, disrupts the quantum state. Free fall eliminates gravity's effect. For those 2 seconds, the atoms experience weightlessness. The BEC expands perfectly. Quantum effects manifest cleanly without gravitational contamination. Simulations suggest 17 seconds might be possible in orbit. A satellite-based cold atom experiment could maintain these temperatures longer than any ground facility. Several space agencies are developing exactly such missions. The International Space Station already hosts the Cold Atom Laboratory. NASA's facility for studying ultra-cold atoms in microgravity, not as cold as Bremann's record, but sustained for much longer. days instead of seconds. What can you do with sustained ultra-cold atoms in space? Test general relativity more precisely than ever possible on Earth. Search for violations of fundamental symmetries. Detect gravitational waves with unprecedented sensitivity. Cold atoms become exquisitely sensitive measuring devices. They respond to tiny forces, minute accelerations, subtle gravitational variations, all the things that get lost in thermal noise at higher temperatures. Atomic clocks already use cold atoms, the most accurate timekeeping devices ever created. They lose less than 1 second in 300 million years. That precision enables GPS tests of relativity, fundamental physics experiments. Colder atoms mean better clocks. Every factor of 10 closer to absolute zero improves timekeeping precision. Future atomic clocks might lose 1 second in the age of the universe. Time measured with quantum-level accuracy. Gravity sensing with cold atoms could revolutionize geology. Find underground water, detect mineral deposits, map Earth's gravitational field with unprecedented resolution. All because ultra-cold atoms respond measurably to tiny gravitational variations. The military is interested too. Submarines navigate using inertial guidance. Accelerometers track every movement to calculate position. Current systems drift over time. Cold atom accelerometers might solve that problem. Navigation without GPS, without any external signal. But perhaps the deepest impact lies elsewhere, in understanding quantum mechanics itself. Quantum theory works spectacularly well. Its predictions match experiments to extraordinary precision. Yet fundamental questions remain. What is wave function collapse? How does measurement work? What's the boundary between quantum and classical? Ultra-cold atoms let us probe these questions. Create macroscopic quantum states. Push quantum systems to larger and larger scales. Find where quantum mechanics transitions to classical behavior. Schrödinger's cat isn't just a thought experiment anymore. Quantum superposition of massive objects is achievable with ultra-cold systems. Not cats yet, but molecules, clusters, increasingly complex systems demonstrating quantum behavior. Each advance toward absolute zero expands the regime where we can test quantum mechanics, where we can see if the theory holds at scales it was never designed for, where we might find cracks in our understanding. That's the real value of extreme cold. Not just applications, though those matter. Not just records, though those drive progress. The fundamental expansion of accessible physics. Temperature determines what states of matter exist, what phenomena are visible, what experiments are possible. Higher temperatures reveal nuclear physics. Lower temperatures reveal quantum mechanics. We've explored both extremes. Particle accelerators reach temperatures exceeding those in the early universe. Conditions moments after the Big Bang. Energy densities where quarks and gluons swim free. At the other extreme, we approach absolute zero, the realm where quantum mechanics completely dominates, where thermal energy no longer masks quantum effects, where new states of matter emerge. The universe naturally provides both extremes. Stellar cores burn at millions of degrees. The Boomerang Nebula chills to 1 Kelvin. Nature shows us what's possible. Humanity adds control. We create these conditions deliberately, in laboratories, on demand, for specific purposes. That's the transformation, from observation to manipulation. But we're still learning. Colossus, the massive dilution refrigerator under construction at Fermilab, will dwarf current systems. 5 cubic meters of cooling volume, 15 times larger than typical commercial units. Why build something so enormous to cool more qubits, more superconducting cavities, more detectors? Scale matters for quantum computers. 1 qubit isn't useful. 100 qubits hint at capability. 1 million qubits might revolutionize computing. Current quantum computers have dozens of qubits, maybe a few hundred, nowhere near the millions needed for practical algorithms. Scaling requires bigger cryogenic infrastructure. Colossus represents that scaling, the infrastructure for quantum computers that might actually matter, for detectors sensitive enough to find dark matter, for experiments that need ultra-stable cryogenic environments. It's scheduled for completion in 2025. Then we'll see if massive scale changes what's possible at ultra-low temperatures. If quantum computers can finally demonstrate clear advantages. If new physics emerges from better detectors. The pursuit of cold drives technology forward. Every record broken required innovation, new techniques, better insulation, sophisticated control systems. Understanding that transfers to other fields. Medical imaging improved from superconductivity research. Quantum computing might solve problems classical computers can't touch. Precision measurement enables tests of fundamental physics. The applications ripple outward, but fundamental questions remain. Why does matter behave quantum mechanically? Why does temperature connect to entropy so deeply? What happens at absolute zero? That last question has an answer now. Nothing happens at absolute zero, because you can't get there. Thermodynamics forbids it. The third law protects that boundary absolutely. Yet we keep trying. Each generation pushes closer, from liquid helium to dilution refrigerators, to laser cooling, to expansion cooling in free fall. Each technique extends the frontier. 38 trillionths of a degree above absolute zero sounds impossibly close. It is impossibly close by everyday standards. Yet it's still infinitely far from zero itself, still separated by a gulf that cannot be crossed. That gulf contains all the quantum mechanics we're still discovering, all the phenomena that emerge as thermal energy approaches its minimum, all the physics that operates at reality's lowest energy scales, the coldest place in the universe, whether natural or artificial, is wherever we're currently probing those phenomena. Wherever scientists push hardest against absolute zero's unreachable boundary. Wherever new physics waits to be discovered in the realm of extreme cold. And that place keeps getting colder. Measurement itself becomes the problem. You're trying to detect thermal energy that barely exists. Your thermometer, any thermometer, interacts with what it measures. That interaction adds energy. At trillionths of a degree, the act of measuring might warm your sample more than the temperature you're trying to detect. Quantum mechanics makes this worse. Heisenberg's uncertainty principle limits precision fundamentally. You can't know both position and momentum of a particle perfectly. Near absolute zero, where quantum effects dominate everything, this uncertainty translates directly into temperature uncertainty. Your measurement device exists in the same quantum realm you're studying. So we measure indirectly, through magnetic susceptibility, through spectral lines, through quantum state populations. Each method has limitations. Each adds uncertainty. The closer to zero, the harder distinguishing zero from almost zero becomes. With current technology, we couldn't identify absolute zero if we somehow reached it. The measurement precision required doesn't exist yet. Maybe can't exist. That's profoundly frustrating for experimentalists who've spent careers chasing this limit. But there's beauty in the chase itself. Each technique invented for reaching lower temperatures taught us something fundamental about matter. Dilution refrigerators revealed helium's quantum properties. Laser cooling demonstrated momentum transfer at quantum scales. Evaporative cooling in magnetic traps showed how to manipulate atoms with unprecedented control. The Boomerang Nebula taught different lessons. Nature accomplishes extreme cooling through violence, a stellar collision. Mass ejected at 500,000 kilometers per hour. Expansion so rapid it overwhelms cosmic microwave background radiation trying to warm it. That's the opposite of laboratory techniques. Labs cool through careful control, isolation, minimizing external influences. Nature cools through chaos, maximum external influence, catastrophic events. Yet both approaches reach similar temperatures. The nebula hits 1 Kelvin naturally. Labs reach trillionths of a Kelvin artificially. Different methods, comparable results. That suggests something fundamental about how cooling works at extreme limits. Temperature measures average kinetic energy. Cooling means removing that energy. But where does it go? Energy can't be destroyed, only transferred. Hot objects radiate energy. Expanding gases do work against their surroundings. Phase transitions absorb energy into structural changes. The Boomerang Nebula uses expansion. Gas blown outward does work against gravity and surrounding pressure. That work costs energy. The expanding gas pays that cost by cooling. Same principle as compressed air getting cold when released, just scaled up enormously. Lab techniques are more varied. Dilution refrigerators transfer heat through helium phase separation. Laser cooling transfers momentum through photon absorption. Evaporative cooling removes the hottest atoms. Adiabatic demagnetization lets magnetic fields carry away energy. Each method exploits different physics, but all share one feature: they move energy elsewhere, into the environment, into ejected particles, into magnetic fields, into photons. Cooling isn't removing energy from existence. It's relocating energy to places that don't affect your thermometer. That's why perfect isolation matters. Heat leaks destroy ultra-low temperatures instantly. A single stray photon carries enough energy to warm a Bose-Einstein condensate significantly. Vibrations from footsteps traveling through the floor can disrupt experiments. Even cosmic rays pose problems. Cori in Italy understood this. They built their detector deep underground, miles of rock overhead, shielding from cosmic radiation. Then they surrounded their cubic meter of copper with layer after layer of insulation. Lead shields, copper shields, multiple nested chambers. Each layer blocks different heat sources. The result? 400 kilograms held at 6 millikelvin for over 2 weeks. That's engineering triumph. Not just reaching that temperature, maintaining it, against Earth's warmth, against radioactive decay in surrounding rock, against cosmic background radiation. Compare that to the Bremen Tower experiment. They held 38 trillionths of a degree for 2 seconds. 2 seconds. Then gravity and environmental influences ended it. In space, simulations suggest 17 seconds might be possible. Still brief, still fragile. Why so difficult? Because coldness is absence. Heat is presence. Heat naturally spreads. Cold doesn't spread. It's simply where heat hasn't reached yet. Fighting that requires constant effort, constant energy input. Paradoxically, maintaining cold requires heat elsewhere. Your refrigerator demonstrates this daily. Its interior stays cold because its back stays hot. Heat pumped from inside gets dumped outside. The total system warms the room. Net energy increases. Entropy increases. That's thermodynamics. You can move heat around, concentrate coldness here by spreading warmth there. But the universe's total thermal energy can't decrease. Cryogenic systems follow the same rules, just more extreme. Dilution refrigerators dump heat at multiple stages. Each stage handles different temperature ranges. Each requires power. Lots of power. Colossus will need massive refrigeration capacity, not to generate cold, to move heat. That's the real cost of extreme cold. Not the low temperature itself, the infrastructure that maintains it, the energy that perpetually pumps heat away, the isolation that prevents heat returning. The Boomerang Nebula doesn't face these costs. It's not maintaining its temperature against anything. It's still cooling, still expanding, still doing work. Eventually it'll reach equilibrium with the cosmic microwave background, then it'll slowly warm. The universe's background temperature provides a floor. Natural processes can't go lower without external work, except the universe itself is cooling. The cosmic microwave background temperature drops as space expands. Currently, 2.7 Kelvin. In the far future, it'll be lower, much lower, eventually approaching zero as expansion continues forever. If that happens, if expansion never stops, the universe's ultimate fate is cold, infinitely cold. Every galaxy isolated, every star burned out, every black hole evaporated. Only diffuse radiation stretched to infinite wavelengths. Temperature approaching absolute zero across all space. That's the heat death scenario. Maximum entropy, minimum temperature. Nothing left to happen because all energy differences have equalized. No gradients to drive processes. No structure. No complexity. Just uniform coldness everywhere forever. We're nowhere near that. The universe is 13.8 billion years old. Heat death requires timescales beyond comprehension. 10 to the power of 100 years or more. Google years, numbers that make billions seem instantaneous. But it's the logical endpoint if current cosmology holds. Dark energy accelerates expansion. Galaxies recede. Eventually, even light from neighboring galaxies won't reach us. Each galaxy becomes isolated, alone in an expanding void, cooling, slowing, dying. Inside those isolated galaxies, local processes continue temporarily. Stars form and die. Planets orbit. Perhaps civilizations arise and fall. But the surrounding universe grows colder, darker, emptier. This connects to why studying extreme cold matters. We're not just measuring temperatures. We're probing how the universe behaves at its lowest energy states, understanding what happens when thermal energy nearly vanishes, learning physics that will eventually dominate everything. Quantum mechanics rules at low temperatures. Classical physics becomes inadequate. Particles behave collectively. Superfluidity emerges. Superconductivity appears. New states of matter form. This isn't academic curiosity. It's understanding reality's fundamental nature. The quantum realm is our universe's foundation. High temperatures mask it. Thermal energy overwhelms quantum effects. Particles behave classically because quantum coherence gets destroyed by heat. Cool things down and the mask drops away. Quantum mechanics emerges from hiding. That's what ultra-cold experiments reveal. Not exotic exceptions to physics, but physics itself. The rules that always apply, but only become visible when thermal noise stops drowning them out. Superconductivity isn't special. It's what happens when you let quantum mechanics work without interference. Same with Bose-Einstein condensates. Same with superfluidity. These aren't weird states matter enters. They're natural states that high temperatures prevent. Cool matter down, and you're not creating strangeness. You're removing the conditions that suppressed quantum behavior. This perspective shift matters. It means quantum mechanics isn't about small things. It's about cold things. Or rather, it's universal. But thermal energy hides it at everyday temperatures. The weirdness we associate with quantum physics is just physics being itself. Heat makes it appear classical. Cold reveals the truth. So pursuing absolute zero isn't about reaching some arbitrary limit. It's about understanding matter's natural state. What atoms do when nothing interferes. How fields behave at minimum energy. What structure emerges from quantum mechanics alone. We can't get all the way there. The third law prevents it, but we can get close enough. Close enough that quantum effects completely dominate. Close enough that thermal energy becomes negligible. Close enough to see what reality looks like without heat's distorting influence. That's the real achievement of ultra-cold physics, not the temperature numbers themselves. But what those temperatures let us observe: quantum mechanics operating nakedly, matter behaving according to probability waves, energy quantized into discrete levels, uncertainty principle visible macroscopically. Future technologies will exploit this. Quantum computers need it. Precision sensors require it. Novel materials demand it. Understanding how to create and maintain extreme cold isn't just scientific, it's practical. Essential for emerging technologies. Which brings us back to Colossus and similar facilities. Their infrastructure for future discoveries. Platforms for experiments we haven't imagined yet. The way particle accelerators enabled discoveries beyond what their builders anticipated. Nobody building the first cloud chambers knew they'd discover antimatter. Nobody constructing early particle accelerators predicted the zoo of subatomic particles they'd find. Infrastructure enables discovery. You build capability, then see what it reveals. Colossus provides capability. 5 cubic meters of cooling volume, stable millikelvin temperatures, room for thousands of quantum devices. What will researchers discover there? What phenomena emerge at those temperatures in that environment? What technologies become possible? Unknown. That's why you build it. To find out. To enable experiments that current facilities can't accommodate. To scale up from proof of concept to practical application, from dozens of qubits to thousands, from laboratory curiosities to functional devices. The coldest place in the universe, whether natural or artificial, keeps revealing new physics. The Boomerang Nebula showed us stellar violence creates extreme cold. Laboratory experiments show us quantum mechanics emerges from it. Future facilities will show us what we haven't yet imagined. Human response. The article discusses script_1 and script_2. Based on the detailed AVD optimization guidelines and the previous part ending, generate part 7 of the script about the coldest place in the universe. This should be exactly 2,250 words and maintain perfect continuity with the previous part's ending. That vision extends beyond quantum computers. Precision measurement becomes possible at extreme cold. Atomic clocks tick more accurately. Gravitational wave detectors gain sensitivity. Any experiment where thermal noise interferes benefits from going colder. Consider atomic clocks. They already measure time to nanosecond precision, but at room temperature, atoms jiggle randomly. That jiggling introduces uncertainty. Cool those atoms to microkelvin temperatures, and suddenly your clock becomes 1,000 times more precise. GPS satellites rely on atomic clocks. More accurate clocks mean better navigation, better synchronization of communication networks, more precise scientific measurements. Gravitational wave observatories face similar limits. LIGO detected ripples in spacetime from colliding black holes. Incredible achievement. But thermal noise in the mirrors limits sensitivity. Cool those mirrors to millikelvin temperatures and you detect fainter signals. Smaller black holes, more distant events, earlier moments in cosmic history. Material science transforms at low temperatures. New compounds exhibit properties impossible at room temperature. Exotic superconductors that might revolutionize power transmission. Superfluids that flow without friction. Topological materials that could enable fault-tolerant quantum computing. You can't study these materials at normal temperatures. They don't exist there. Their defining properties emerge only when thermal energy stops disrupting quantum coherence. So to understand them, to potentially use them, you need facilities like Colossus, places where you can create, maintain, and manipulate matter in these extreme states. The Boomerang Nebula achieved its record naturally, through stellar violence and physics operating at cosmic scales. No intention behind it, just consequence of how dying stars eject matter and how rapidly expanding gas cools. Nature accidentally created the coldest place in the universe, but humans achieved something arguably more remarkable. We intentionally created temperatures colder than that nebula, not through stellar scale events, through clever exploitation of quantum mechanics, laser cooling, magnetic trapping, dilution refrigeration. We bent the rules of thermodynamics to approach absolute zero more closely than any natural process. The Bremen experiment reached 38 trillionths of a degree above absolute zero. That's colder than anywhere in the cosmos, colder than interstellar space, colder than the darkest void. For 2 seconds, a cloud of rubidium atoms in a German laboratory represented the coldest matter in the universe. Think about that progression. Lord Kelvin calculated absolute zero in 1848. Couldn't imagine actually approaching it. Just mathematical consequence of his equations. Now we routinely create temperatures millions of times colder than outer space. We've gone from theoretical limit to laboratory reality in less than 2 centuries. And we're not done. Simulations suggest those Bremen experiments could maintain record temperatures for 17 seconds in microgravity. Space-based cold atom laboratories are already planned. The Cold Atom Lab on the International Space Station operates continuously. Future missions will go further. Why? Because each improvement in how cold we can go enables new science. Quantum effects become more pronounced. Measurements grow more precise. Phenomena impossible at higher temperatures become accessible. The frontier keeps expanding. But here's what's fascinating about the competition between natural and artificial cold. The Boomerang Nebula maintains its temperature constantly. It's been that cold for over 1,000 years. Will remain cold for thousands more. Enormous volume of space at 1 degree Kelvin. Sustained naturally through stellar physics. Laboratory experiments achieve lower temperatures but briefly. 2 seconds, maybe 17 in microgravity. Then thermal fluctuations creep back in. You have to restart the cooling cycle. Constant energy input required, elaborate isolation from the environment, sophisticated control systems. Nature wins on duration and scale. Humans win on absolute coldness. Different achievements, both impressive in their own way. Both teach us about the universe's temperature extremes. The cosmic microwave background sets a floor for natural temperatures. 2.7 Kelvin everywhere in space. Leftover radiation from the Big Bang. You can't passively cool below that. The universe itself is that warm. The Boomerang Nebula only beats it through active cooling. That fierce wind blasting away heat faster than cosmic radiation replaces it. Stop that wind and the nebula would warm up. Eventually reach equilibrium with the CMB. Return to 2.7 Kelvin like everywhere else. So even nature's coldest achievement requires continuous energy expenditure. Just like our laboratory refrigerators, this reveals something fundamental. Fighting entropy costs energy, always. Whether you're a dying star or a dilution refrigerator, maintaining low temperatures requires constant work against the universe's tendency toward thermal equilibrium. Second law of thermodynamics never stops applying, yet both nature and humans persist in creating cold. Stellar physics drives one. Scientific curiosity drives the other. The results differ in scale and duration, but not in principle. Both represent ordered systems maintained far from equilibrium through energy input. Future cold experiments will likely move to space. Microgravity environments offer advantages. No convection. Easier magnetic trapping. Longer observation times. The International Space Station already hosts quantum experiments. Dedicated cold atom satellites are proposed. Imagine a laboratory facility in permanent shadow at lunar South Pole. Perpetual darkness, natural cooling to 40 Kelvin. Start your refrigeration from there instead of room temperature. Reach millikelvin temperatures more easily. Maintain them longer. Conduct experiments impossible on Earth. Or place dilution refrigerators in deep space, far from solar radiation, natural starting temperature near cosmic background. Less thermal isolation required. More efficient cooling. Potentially larger experimental volumes than ground-based facilities can achieve. These aren't science fiction. They're engineering challenges. Expensive ones, but not fundamentally impossible. We've already demonstrated quantum experiments in space. Scaling up is difficult but feasible. The scientific payoff would be enormous. Meanwhile, the Boomerang Nebula continues its cosmic demonstration. Stellar death produces extreme cold. Binary star interactions make it even colder. Natural processes operating according to physics we understand. Yet achieving temperatures we struggle to match artificially. In 1,000 years, that nebula will still be cold. Our laboratory equipment will be museum pieces. The specific experiments we run today will seem primitive, but the fundamental pursuit continues. Understanding matter at its coldest. Exploring quantum mechanics without thermal interference. Pushing closer to absolute zero. We can't reach it. Third law prevents that. But we can keep approaching. Each decimal place closer reveals new physics. Each improvement in cooling technology enables new experiments. The journey toward absolute zero is infinite. There's always another digit to chase. That pursuit connects the largest and smallest scales. Cosmic nebulae and trapped atoms, stellar physics and quantum mechanics, natural processes and human engineering, all converging on the same question. What happens when you remove heat from matter? The answer keeps surprising us. Superconductivity, superfluidity, Bose-Einstein condensation, quantum computers. Each discovery emerged from going colder. Each revealed physics hidden at room temperature. Each suggested new applications we hadn't imagined. So when you hear about the coldest place in the universe, remember it's not just one place. It's a competition between nature and artifice, between stellar violence and laboratory precision, between sustained cold across light years and brief cold in microgram samples. The Boomerang Nebula wins for natural achievement. Bremen experiments win for absolute temperature. Colossus and future facilities will win for practical application. Each represents a different aspect of humanity's relationship with extreme cold. But they all point toward the same truth. Cold isn't absence, it's revelation, not emptiness, but clarity. When you remove thermal noise, quantum mechanics emerges. The universe's fundamental operating system becomes visible. Physics stops hiding behind heat's distortions. That's why we build bigger refrigerators, why we chase colder temperatures, why we study dying stars 5,000 light years away. Not because cold itself matters, because what cold reveals matters. The hidden quantum reality underlying everything. The natural state of matter when nothing interferes. Absolute zero remains unreachable, but approaching it teaches us what the universe really is. Not the hot, chaotic place of everyday experience, but a quantum system where probability waves collapse into reality, where particles tunnel through barriers, where matter behaves according to rules that seem impossible until you cool it enough to observe them. The coldest place in the universe isn't really about temperature. It's about understanding, about seeing reality without thermal camouflage, about discovering what physics looks like when nothing obscures it. Every Kelvin we remove strips away another layer of apparent complexity, reveals deeper simplicity underneath. So we keep cooling, keep measuring, keep building larger facilities and more sensitive instruments, keep studying natural cold in cosmic nebulae and artificial cold in laboratory chambers. The pursuit never ends because there's always more to discover. Always another quantum phenomenon waiting to emerge at lower temperatures. Always deeper understanding available if we can just get a little bit colder. Human response. You are an expert YouTube scriptwriter that writes scripts in your own words. You will be creating scripts that will be read aloud by a text-to-speech AI directly. Ensure your output has proper punctuation and does not plagiarize. Do not include any parenthetical text or stage directions. Do not include a title or headers. Output the script only, no commentary or additional text. 200,000. There's something profound about standing at the edge of absolute zero. Not physically, that's impossible, but conceptually, intellectually. Understanding that we've pushed matter to temperatures where the normal rules break down completely. The Boomerang Nebula sits out there in the constellation Centaurus, 5,000 light years away. Still cooling, still expanding, still maintaining its title as nature's coldest achievement. 1 degree Kelvin, colder than empty space itself. A cosmic accident that revealed how extreme natural processes can become. But here on Earth, in laboratories scattered across the globe, scientists have exceeded that. 38 trillionths of a degree above absolute zero. Not for long, just 2 seconds, but long enough to prove something remarkable. Intelligence and understanding can accomplish what raw cosmic violence cannot. That's the real story here. Not which is colder, not who wins the competition, but what we've learned from both. The nebula taught us that stellar death can create extremes we never anticipated. That binary star collisions release enough gravitational energy to blast matter into space at 500,000 kilometers per hour. That expansion on such scales produces cooling effects visible across interstellar distances. Natural physics operating at maximum intensity. Laboratory experiments taught us something different. That precision beats power. That understanding quantum mechanics lets us manipulate individual atoms with laser light. That clever engineering can create conditions more extreme than stellar catastrophe. That we don't need violence when we have knowledge. Both lessons matter. Both reveal aspects of how the universe works. Temperature isn't just a number, it's a window into matter's fundamental behavior. Cool something down, and you're not just making it cold. You're removing the thermal noise that hides quantum mechanics, stripping away the chaos that makes matter appear classical. What emerges is strange, particles that behave like waves, waves that behave like particles, matter that flows without friction, electricity that conducts without resistance, atoms that merge into single quantum entities. All the weirdness quantum theory predicted, but everyday temperatures conceal. This isn't academic curiosity. Quantum computers depend on it. Atomic clocks require it. Precision sensors need it. Future technologies we haven't imagined yet will exploit it. The coldest temperatures humanity can achieve aren't just records, they're tools, enabling capabilities impossible at any higher temperature. Colossus represents that future. 5 cubic meters of space cooled to millikelvin temperatures. Room for thousands of quantum devices. Infrastructure for experiments that current facilities can't accommodate. When it comes online in 2025, it won't just be the world's largest dilution refrigerator. It'll be a platform for discoveries we can't predict yet. That's how progress works. You build capability first, then see what it enables. Particle accelerators discovered particles their builders never anticipated. Telescopes revealed galaxies nobody knew existed. Cryogenic facilities will uncover physics we haven't imagined. The third law of thermodynamics says we'll never reach absolute zero. Can't be done. Not in finite time with finite energy. That boundary remains forever out of reach. But approaching it keeps yielding discoveries. Each decimal place closer reveals new phenomena. Each improvement in cooling technology opens new experimental possibilities. We've gone from liquid helium to dilution refrigerators, to laser cooling, to expansion cooling in free fall. Each technique pushed closer to absolute zero. Each revealed physics hidden at higher temperatures. The progression continues. Space-based experiments, larger facilities, better isolation, more precise control. 38 trillionths of a degree today, maybe 38 quadrillionths tomorrow, perhaps quintillionths eventually. The numbers keep shrinking. The frontier keeps advancing. There's always another digit to chase. But here's what really matters. We're not chasing cold for its own sake. We're chasing understanding. Every Kelvin we remove strips away another layer of thermal camouflage, reveals quantum mechanics more clearly, shows us how matter truly behaves when nothing interferes. That's the universe's deepest secret. Reality is quantum, always has been, always will be. We just can't see it at everyday temperatures. Heat drowns out the quantum signal, makes everything appear classical, solid, deterministic, predictable. Cool things down and the illusion fades. Quantum mechanics emerges from hiding. Probability waves become visible. Superposition becomes measurable. entanglement becomes exploitable. The universe stops pretending to be classical and reveals its quantum nature. The Boomerang Nebula stumbled into this accidentally. Stellar physics created conditions where quantum effects might become important, though probably not. 1 degree Kelvin is still too warm for most quantum phenomena. Still too much thermal energy disrupting coherence. But it pointed the way, showed that nature can create extreme cold through expansion, that rapidly moving gas bleeds away thermal energy faster than anything can replace it, that with enough violence you can cool matter below the universe's background temperature. We took that lesson and refined it, removed the violence, added precision, controlled the expansion, manipulated quantum states directly, achieved temperatures 1 trillion times colder than stellar death produces. Not through accident, but through understanding. That's humanity's contribution, not matching nature's power, exceeding it through knowledge, not competing with stellar explosions, outperforming them through clever physics. The universe can be violent, we can be precise. Precision wins, so the coldest place in the universe keeps moving. Used to be the Boomerang Nebula, then MIT's laboratory, then NIST's facility, then Bremen's drop tower. Tomorrow it might be a satellite experiment. Next year, Colossus. Eventually something we haven't built yet. The location changes. The temperature drops. But the goal remains constant. Understanding matter at its most fundamental level. Seeing quantum mechanics without thermal interference. Discovering what the universe really is beneath heat's distorting influence. Absolute zero waits at the end of this journey. Unreachable, but infinitely approachable. An asymptote we chase forever without arriving. That's fine. The journey itself reveals more than reaching the destination ever could. Each step closer teaches us something new. Each improvement in cooling technology enables discoveries that reshape our understanding. We've learned that matter has states beyond solid, liquid, gas, and plasma. That superfluidity and superconductivity aren't exotic exceptions, but natural consequences of quantum mechanics at low temperature. That Bose-Einstein condensates demonstrate macroscopic quantum behavior. That quantum computers require cold to function. We've discovered that precision timekeeping needs ultra-cold atoms. That gravitational wave detection improves at lower temperatures. That material properties transform when thermal energy stops disrupting quantum coherence. That technologies we can barely imagine today will depend on capabilities we're developing now. The Boomerang Nebula sits out there as reminder. Nature got there first, created extreme cold through stellar violence billions of years before humans existed. It'll remain cold long after our current experiments are forgotten. Cosmic timescales dwarf human achievements, but we're not competing with cosmic timescales. We're building understanding, creating capability, enabling future discoveries. The nebula is cold. Our experiments are colder. Both teach us about the universe. Both matter. Temperature measures disorder. Heat represents chaos. Cold represents order. Absolute zero represents perfect quantum order, where thermal randomness completely vanishes. We can't reach it, but we can get close enough to see what perfect order looks like, close enough to exploit it for technology, close enough to understand reality's quantum foundation. That understanding changes everything, not just physics, not just technology, our entire conception of what matter is, what temperature means, how the universe operates at its deepest levels. Cold isn't absence of heat, it's revelation of quantum mechanics. its clarity emerging from chaos, its reality showing its true face. So we keep cooling, keep measuring, keep building larger facilities and more sensitive instruments, keep studying cosmic cold in distant nebulae and artificial cold in laboratory chambers. The pursuit continues because there's always more to discover, always another quantum phenomenon waiting to emerge, always deeper understanding available. The coldest place in the universe is wherever we're currently pushing hardest against absolute zero's unreachable boundary. Right now, that's Bremen's drop tower. Soon, it'll be Colossus. Eventually, somewhere else. The location matters less than the pursuit itself. The temperature records matter less than what those temperatures reveal. We're learning to see quantum mechanics nakedly, to observe matter without thermal camouflage, to understand the universe as it truly is, rather than how heat makes it appear. That's the real achievement, not the temperature numbers, not the records broken, the insight gained, the physics revealed, the technologies enabled. Absolute zero remains forever out of reach, but approaching it keeps teaching us what we didn't know, keeps revealing physics we didn't expect, keeps enabling technologies we hadn't imagined. The journey never ends because the frontier keeps expanding. There's always another decimal place, always another discovery, always more to understand. That's why the coldest place in the universe matters. Not because cold itself is valuable, because what cold reveals transforms our understanding of reality itself. Every Kelvin removed strips away another layer of apparent complexity, shows us the quantum simplicity underneath, demonstrates that the universe's true nature is stranger and more beautiful than everyday experience suggests. The Boomerang Nebula proved nature can create extreme cold. Laboratory experiments proved we can exceed it. Future facilities will prove we can exploit it. The progression continues. The temperatures drop. The understanding deepens. The applications multiply. And absolute zero remains where it's always been. Unreachable, but endlessly approachable. The ultimate limit that defines how cold anything can become and how clearly we can see quantum mechanics in action.